A black hole is not a doorway to another life. It is not a tunnel to heaven. It is not a secret staircase into another universe that science has already confirmed. It is something stranger, colder, and more difficult to escape from. A place where gravity has bent space-time so deeply that every possible future begins to point inward. And the most frightening part is this. If you fell into the right kind of black hole, you might cross the point of no return without feeling the exact moment it happened. No wall, no impact, no warning from nature. Just a quiet crossing into a region from which your story can never return. Albert Einstein did not invent black holes as monsters. He was trying to solve a problem about gravity. Before him, Newton had described gravity as a force, something that pulls planets, moons, and apples. Newton's equations worked beautifully. They explained why Earth orbits the sun and why objects fall to the ground. But Newton's picture left a mystery behind. How could the sun pull Earth across empty space without anything carrying that influence? Einstein gave gravity a deeper meaning. In his general theory of relativity, gravity is not just a pull, it is the curvature of space-time. Mass and energy bend the stage of the universe, and objects move through that curved stage along the straightest paths available to them. Around Earth, this curvature is gentle. Around the sun, it is stronger. But around a black hole, space-time is bent so severely that escape stops being a normal idea. This is where the name becomes misleading. A black hole is not a physical hole in space. It is not an empty tunnel with walls. It is a region surrounded by an invisible boundary called the event horizon. Outside that boundary, light can still escape. Inside it, even light cannot reach the outside universe. And because light is the fastest messenger reality allows, if light cannot escape, nothing else can carry information out either. That is why black holes are black. Not because they are painted dark, but because they silence every signal from within. But if nothing comes out, how do we know black holes exist? Einstein's theory predicted the possibility, but for a long time, many scientists doubted nature would actually create such extreme objects. Then astronomers began seeing their fingerprints, stars orbiting something invisible, gas spiraling around compact dark centers, jets of energy blasting from galactic cores, gravitational waves from collisions between unseen massive objects. And in recent years, images of glowing gas bent around the shadow of supermassive black holes. We do not see the inside. We see what black holes do to everything around them. A black hole can form when a very massive star dies. During most of its life, a star is a battle between two forces. Gravity pulls inward. Nuclear fusion pushes outward with heat and radiation. For millions of years, the star holds itself up. But when its fuel runs out, the pressure supporting it can fail. The core collapses. If enough mass is packed into a small enough region, no known force can stop the collapse from forming an event horizon. This does not happen to every star. Our sun is not massive enough to become a black hole. Billions of years from now, it will expand into a red giant and eventually leave behind a white dwarf, not a black hole. But if we imagine, as a thought experiment, that the sun could somehow be compressed into a black hole without changing its mass, Earth would not suddenly be sucked in like dust into a vacuum cleaner. Gravity far away depends mostly on mass. If the mass stayed the same, Earth would continue orbiting the same center. The real disaster would be the loss of sunlight. The planet would freeze. Life would end, not because the black hole pulled harder from far away, but because the sun's light was gone. This is an important correction. Black holes are not cosmic vacuum cleaners that eat entire galaxies just because they exist. A black hole only dominates the region close to it. Our Milky Way has a supermassive black hole at its center called Sagittarius, a star, with about 4 million times the mass of the Sun. Yet the galaxy is not being swallowed whole. Stars orbit the galactic center just as planets orbit stars. Gravity organizes motion, it does not automatically devour everything. But close to a black hole, the story changes completely. Imagine you are falling toward a supermassive black hole, millions or billions of times heavier than the sun. We choose a giant because the experience depends on size. Near a small stellar mass black hole, the gravity can change so sharply over short distances that your body might be torn apart before you even reach the event horizon. Near a supermassive black hole, the horizon is so wide that the difference in gravity between your head and feet at the boundary can be gentle enough for you to cross alive. That makes the journey more terrifying, not less, because it means you get time to understand what is happening. At first, the black hole does not look like a simple black circle. If there is hot gas around it, that gas forms an accretion disk, a violent whirlpool of matter orbiting just outside the horizon. The gas is heated by friction, pressure, and extreme motion until it glows with incredible energy. The center is dark, but the edge can shine brighter than stars. If the black hole is actively feeding, radiation could destroy your spacecraft before gravity does. So imagine a quieter black hole, one that lets you approach without being burned away. Even then, the view through your window would become impossible. Stars behind the black hole appear where they should not be. Their light bends around the darkness before reaching you. A galaxy hidden behind the black hole may stretch into a curved arc. The same star may appear multiple times because its light has traveled along different curved paths through space-time. Einstein would have understood the meaning immediately. The black hole is not just pulling matter. It is bending the road that light itself must follow. As you fall closer, your cabin may still feel calm. Your clock ticks normally. Your breathing continues. A loose object floats beside you. If the spacecraft is freely falling, you do not feel weight the way you feel it standing on Earth. You and the ship are following the same curved path together. This is Einstein's equivalence principle. Free fall can locally feel like floating in empty space. Gravity has not vanished. You have simply stopped resisting the fall. But this calm is deceptive. If you tried to hover near the horizon instead of falling, your engines would need to fight the black hole every second. The closer you tried to remain still, the more violent the required acceleration would become. You would be crushed into your seat by the force needed to resist the natural path through space-time. Falling feels peaceful because you are surrendering to the geometry. Hovering feels violent because you are fighting it. Outside your window, the blackness grows, but it does not grow like a planet or a moon. It seems to bend upward around you. More and more of the outside universe is squeezed into a smaller, distorted patch of sky. Light that once came from ordinary directions is redirected. The view behind you begins to shrink, as if the rest of existence is being folded into a bright window above the darkness. Then you approach the photon sphere. This is not the event horizon. It is not a solid shell. It is a region where gravity is strong enough for light to orbit the black hole on unstable paths. A beam of light there is balanced on a knife edge. A slight outward shift lets it escape. A slight inward shift sends it into darkness. Near this region, vision becomes unreliable. Light from behind you can curve around and appear in front of you. Stars become rings and arcs. The universe turns into a distorted mirror made not of glass, but of space-time. And still, inside your ship, you may not feel the true danger. That is the strange power of Einstein's theory. Your local experience can feel normal, while the global structure of the universe is becoming impossible. Far away, an observer sees a different story. Suppose your spacecraft sends a steady radio signal back to them. To you, the transmitter works normally. But to the distant observer, the signal slows. Each pulse takes longer to arrive. The light and radio waves leaving your ship must climb out of stronger gravity, and in that climb they lose energy. Their wavelength stretches, their color shifts toward red. Your clock appears slow, your beacon appears delayed, your image becomes dimmer. The outside observer never receives a clean final moment where you cross the event horizon. But you would not remain visibly frozen there forever. That is a common misconception. In practice, your final light becomes increasingly delayed, redshifted, and faint. Very quickly, you disappear from observation. From outside, you fade at the edge. From your point of view, you continue. Both descriptions are true because time is not universal. Near the black hole, your time and the distant observer's time no longer flow together. If a probe remained above you and sent a regular signal, you could watch that signal shift as you descended. It would become evidence that space-time itself is changing the rhythm of clocks. This is not an illusion. It is not bad measurement. It is Einstein's universe. Then comes the event horizon. You expect a border, a flash, a warning, something, but there is no physical surface. The event horizon is not made of matter. It is a boundary in causality. It marks the last place from which light can still escape to the outside universe. Your computer may calculate the crossing. Your eyes may see the outside universe shrink and distort, but your body may feel nothing special at the exact boundary. Then you cross. No crash, no wall, no sound. A moment before, escape was possible in principle. A moment after, it is not. Not because your engines are too weak, but because the direction called out no longer leads outside. On Earth, escape is a speed problem. Launch a rocket fast enough, and it leaves the planet. Inside a black hole, escape is a geometry problem. Even light moving at the fastest speed reality permits cannot follow a future path back to the outside universe. You turn the spacecraft around, you fire the engines. The ship responds. But all you have done is choose a different inward path. You send a final message. It stays inside. You aim a laser outward. It cannot return. The outside universe can still send light falling after you, but you cannot answer. The universe can speak to you. You can no longer speak back. Could someone rescue you with a cable? Suppose a ship outside lowers an impossibly strong tether through the horizon and tries to pull you out. It sounds clever, but Einstein's universe does not allow it. No object is perfectly rigid. When you pull one end of a rope, the other end does not respond instantly. The signal of that pull travels through the material at a finite speed, always below the speed of light. At the event horizon, that limitation becomes absolute. The part inside cannot send information back out. The tether would stretch, break, or fall in. It cannot turn a one-way boundary into a two-way road. The event horizon is not a door with a handle. It is the end of every outward route. Now the gentle part of the fall begins to end. At the horizon of a supermassive black hole, tidal forces may be mild, but deeper inside, they grow. Gravity is not equally strong across your spacecraft. The nose, closer to the center, follows a slightly different path than the tail. Metal strains, the frame twists, instruments fail. Then the same difference reaches your body. If your feet point inward, they feel a stronger gravitational effect than your head. At first, the difference is small, then painful, then fatal. Your body stretches lengthwise and compresses sideways. The famous name is spaghettification, but the word almost hides the horror. It is gravity turning a human being into a stream of matter. For a small black hole, this could happen before the event horizon. For this giant black hole, it happens after you have crossed, where no outside observer can see the final result. The horizon gave you time to witness the fall. It did not give you survival. Ahead lies what general relativity calls the singularity. But here science must be honest. A singularity is not a photographed object. It is not a confirmed tiny point sitting at the center. It is what Einstein's equations predict when space-time curvature grows without limit. The mathematics reaches infinity, and infinity in physics often means our theory has reached its boundary. General relativity explains the horizon. It explains time dilation. It explains why light bends, why distant observers see you fade, and why escape becomes impossible. But near the deepest interior of a black hole, gravity becomes so extreme that quantum physics should matter. We do not yet have a complete confirmed theory of quantum gravity, so your fall becomes more than a death. depth. It becomes a journey to the edge of human knowledge. Einstein's theory carries you almost all the way. Then, near the center, it begins to lose its voice. The horizon acts like a cosmic curtain, preventing the outside universe from seeing what happens where our equations begin to fail. This is why black holes are not just dangerous objects. They are questions written into the structure of the universe. They ask what time really is. They ask what space becomes when it is curved beyond escape. They ask whether information is truly lost or hidden in a way we do not yet understand. They ask where Einstein's theory ends and the next theory must begin. Some people imagine black holes as gateways to other universes or passages beyond time. The honest answer is that we do not know of any confirmed path through a real black hole that would let a person travel safely elsewhere. White holes and wormhole-like structures appear in some mathematical solutions, but they have not been observed as real cosmic doors. The black holes we know from evidence are not proven entrances to another life. They are regions where escape ends and our theories are pushed to their limits. That truth is already strange enough. Return now to the beginning. You are falling toward a black hole. Behind you, the universe races ahead. To a distant observer, your clock slows, your light reddens, and your image disappears. But you do not remain frozen at the edge. You cross. For a while, perhaps the cabin feels calm. Then the curvature grows, the ship fails, your body stretches. And ahead, beyond every outside observer, Einstein's equations point toward a place they cannot fully describe. That is the terrifying lesson. A black hole does not merely trap light, it traps every possible road back. What feels more disturbing to you? Crossing the event horizon without noticing, or knowing the outside universe will never receive your final story? Subscribe to explore more documentaries through Einstein's questions, the questions that still lead us to the edge of reality.